Morning. How are you? All right, so today we are moving to the second part of this course, which is the most interesting and useful part of the course, I guess, for control systems. We are talking about optimal controls now. So before that, we defined different state space representations. We defined controllers, observers, but we never talked about anything optimal in any sense in that course so far. But today we will be talking about optimal controllers and optimal design and what it means and what functions we can minimize and why we need that. So most of the controllers that are in use until today are typically from optimal controls. So many people are still using in classical design, but mainly optimal control design, because first of all, it's very easy from the computational perspective. It's very easy to compute optimal controller. It's very easy to adjust weights in such a way that it will be controllers that you want, and it will produce for you whatever performance you want. And since we have computers now, we don't need to do anything like that by hand. We will do that in that course, a few examples. But in practice, obviously, you're not doing any of these computations by hand. Technically speaking, to find optimal controller, all we need to do is to solve a few nonlinear equations simultaneously. So it's a system of nonlinear equations that we need to solve. But for computer, it's not a big deal. Like by hand, it's difficult. We will see some issues. We will use very simple example. And we will see that even with that simplistic example of 2x2 system, like second order system, it's already becomes system of two quadratic equations, which means you have like two roots for each. You get like 4 different possible solutions to that system. And even getting to the solutions is difficult. But imagine if your system is like 50 by 50. Okay, so you have 50 equations, high order. So it's difficult to solve by hand, but computers do that just using some optimization processes. And we will not get into these details, but we will talk about just how to get there, right? Like what is the solution, why is the solution optimal, and how it all works together. So here's our motivation for doing optimal controls. So why not just to choose particular closed loop, where it will be like particular performance, it will have particular location in stable location within the unit circle for discrete time or in the left semiplane for continuous time. So why not just to choose the poles, to design the controller, practically done, right? We've seen that before. It's not a big deal. It's easy. We have even 3 different ways to do that, right? So the idea is that, yes, you can do that, but unfortunately, if you choose it incorrectly, the location of poles, then your inputs might be huge, which means the input to the system, which is control effort to the system, to your plant, might be too high. And typically, if you want your system, for example, to be very fast, right, you need to supply a lot of energy to the system, right? You need to push it hard. This is natural. But if system is mechanical or electrical or whatever your system is, you have limit on how hard you can push it until it breaks, right? This is natural physics. We cannot avoid that part. So mathematically, it would be great. I mean, you have input of 1 million volts, fine, sure. It will converge in 1 millisecond. Like you have robotic arm, which is moving from that place to that place in 1 millisecond. Sure, mathematically. But physically, it's impossible, right? Because it actually needs time to move. So you cannot make it move without giving it strong power, strong force. But giving it that strong force, you can break it. So you will get to area where actually your computed inputs for your designed controller are not physically possible or not good enough, right? So here becomes a question like how we balance the both. So we want to balance somehow and limit our values for states and for inputs, which means that the input signal, which is U signal, should be limited somehow. So it should be less than particular boundary threshold, right? And all of the states inside the system, also each one of them needs to be within particular boundaries. You don't want like some voltage inside the system to go to 1 million volts or anything like that, right? So you don't want the states to be huge. Some other states you don't care. Like you might have states where you don't care where it will be, and you have some other states where you do care where they need to be, right? For example, if one of your states is location of your card on the rail, right? You don't want it to be like 100 meters from here. You don't want at any point of time this card to be 100 meters from here because you do not have any rails there, okay? So you have rail of 1 meter or whatever. So you don't want it to skyrocket somewhere else and then return back. Because theoretically it will work. It will get you signal and then it concentrates on as a part where you want it to be, right? But physically it will not happen to your real system. So these are the issues that we need to consider. Typically faster convergence means more noise, but this is not an issue. It typically means higher force that you need to apply to the system somehow. And by force, I'm not only meaning like physical force. Sometimes it's voltage, sometimes it's some signal of some kind should be too high for your design, okay? And there is no way that you would know like where to move your poles to make it smaller, to compromise. Like to say, well, maybe it shouldn't be that fast, right? But still I want it to be as fast as possible. Out of all possibilities, I want to choose the poles somewhere where it will be input lower than such and such energy, but the output as fast as possible converging to whatever I want it to converge, okay? So this is the overall idea of optimal controls, where you're trying to find these compromises between reasonable input and reasonable output convergence, all right? This is what is called regulation problem, where you have zero input and you want to converge to zero from some initial conditions as fast as possible without spending too much energy. Okay, so this is the main topic, which is called LQR, linear quadratic regulator, right? And this is optimal controller, state space controller. It's still same state space as we learned before, so it's not some different architecture or anything like that. It's still that K vector, okay? But for that K vector, you're designing K optimal, which would minimize energy of input weighted with energy of the output somehow, okay? And this is optimization criteria that we will be talking about, one of them. All right, so to talk about minimization and optimization in general, you always need to define some optimization criteria, which means it's making no sense whatsoever to say something is optimal without defining based on what cost function, which means there is no such thing as optimal in general. Optimal with regard to particular cost function, and we'll call that cost function J, okay? So the J will be defined like that. So it will be defined here. So you have a regular state space system in, you probably need to open the door, otherwise it's locked from outside, unfortunately. Thank you. So you have regular state space system, okay? And for that state space system, you define the criteria that you want to optimize. So what is the cost function that we are defining here? This J is defined as integral from 0 to infinity in time, this integral in time, on a trajectory of xt and trajectory of ut. And if you remember, ut is what you decide to give, right? This is input of the system, control effort, right? So you are providing that u, which is changing axis, right? This is output of your controller, practically speaking, right? That u is output of your controller. So you decide what u will be. And you are trying to get performance from the y, which is output of the system, or x, which is state of the system. All of them are vectors in that case. So I'm defining generic function, but if it is, for example, CISO system, a single input, or CMOS system, this u is scalar and this u is scalar function, right? So it will be just u squared, right? If u is scalar, then you'll have u of t squared times constant r, and r will be number, scalar number, all right? But for matrix and MIMO systems, it could be u vector. So you might have multiple inputs of u. It could be many u, right? Same thing with x. X is vector, so x transpose is something like that, right? It's like vector of row, X is vector of column, and Q is n by n matrix of weights. So let's see what that thing means one by one. So this part is easier. So think about seesaw system first, which means U is scalar function of T, just some plot, right? So U transpose times R times U is just RU squared. So what is integral from 0 to infinity on U squared? Signals and system schools. What is that? I mean, typically you also see that as absolute value of U, because U might be also complete, but not in our case. It's like integral on U absolute value squared dt. So you have term for that.
Infinity?
No, it's not infinity. I'm asking like, what is that called? Integral on U squared, on signal squared in general. What is integral of signal squared? It's practically area under the plot squared, right? So if it is periodic, obviously it will be infinity, but if it is not periodic and limited in time, short interval of time, you can compute area under the squared plot. So what that would be called, that area?
Area under the curve, did you say?
It's area under the curve, but it has name in signals and systems. And it's coming from circuits, actually, from electrical engineering. That name from physics.
Energy?
It's energy of the signal. And it's coming from similar thing from circuits, from like energy on the resistor. You put in voltage on the resistor, you have current, and V squared divided by I will be whatever you need, okay? So energy will be the integral that you are making in time on the signal, which is coming from circuits, right? So same thing here. This is practically energy of the input or control effort, okay? R is variable, which is weight of that energy, which means how important that energy for us to minimize. All right, so R number, scalar number R, in that case will be like if R is huge, we will be minimizing a lot the input. Why is that? Like this is tricky part here in all optimization theory. Like to understand the reasoning behind like what I'm maximizing and what I'm minimizing here. Like why I'm getting one number bigger, but suddenly this number gets smaller. And like I'm increasing weight of something, but this thing becomes more important, but it becomes smaller actually at the end of the optimization. So think about that like that, okay? So the goal of the optimization is to minimize J, to get J as minimal as possible, okay? And you have relative weights of two components here. We will call that Q and R. So they are, think about that as relative weights between these two parts, okay? One part will have importance Q, another part will have importance R, okay? So if you increase R a lot, you make it 1 billion, okay? So you get 1 billion times energy of input plus some small number times energy of X, some kind, okay? And you want to minimize that sum. What X or U will be minimized more? So you're minimizing the sum of 1 times energy of X plus 1 billion times energy of U. And you're minimizing that sum. So what will be smaller, X or U? What will be minimized more? So you have something like that. You have an integral, which you want minimal of that thing. So here you have alpha times energy 1 plus beta times energy 2. Okay. So what will be beta is larger than alpha, much larger. Okay, so what will be minimized more, this one or this one? When this one is minimal.
And the integral is for the whole thing.
For the whole thing, yes. No, you can minimize this one or this one. Like what will be minimized more, E1 or E2? This is constant and this is constant. So you're not changing them, you're not minimizing them, right? And this constant is huge, this constant is tiny. So to make that entire thing minimal, okay?
Even.
So what will be
Even.
smaller, this one or this one?
Even.
E1 will be smaller?
No, the smaller than E2, as beta is like is larger.
What will be minimized more? Like you can change this one or you can change this one. And you are imposing that this entire thing will be minimum. So what should you minimize more, this one or this one? You should minimize more E2 because 1 billion times something close to 0 only will give you a small number, right? But small number times whatever will be also small enough, okay? So you have to compromise here a little bit because you cannot minimize both of them to 0. It would be ideal if both of them are 0, okay? But you cannot get it, okay? Because they are interdependent also somehow inside. Because, for example, smaller the Y you want to be, like the output want to be, higher the U will be. This is how it works, okay? You need stronger inputs to get smaller outputs as fast as possible, okay? To minimize the overall energy of the output. You need to increase the energy of the input. You need a lot of force to make system to move fast. This is how it works. But, so they are interdependent. But if this number is huge, you minimize more that thing because the multiplication will be smaller. This is how you want it to be, all right? So this is the overall idea that it's kind of, initially it's a little bit against of logic. Like we're thinking like, oh, this number is big, so this should be small. No, this will be small, okay? So higher that number is, smaller that number is, not number function. Area under the plot of square of that function, okay? So this is exactly how it works, which means that if you choose huge R here, you will be minimizing more the input, overall energy of input. And energy of input is practically area under the plot of the entire input from 0 time to infinity time, like for the entire time period, okay? And this typically means that this part will go up. You will have stronger, higher x's. But now for x's, we have their own Q part. So pay attention that this is very well-known thing, which also has name. This is kind of energy of x's, but not only. This is, we talked about that, like what that thing is, especially when Q is positive definite. I gave you that name from linear algebra. How that thing is called X transpose positive definite matrix X. So this is square, quadratic. Quadratic what? This is quadratic form in linear algebra. This is a standard term for X transpose QX. Quadratic form of matrix Q. All right? So quadratic form by definition is positive for positive definite matrices. This is how positive definite matrices are defined in the first place. Okay, that X transpose some matrix X for all X's will be positive. This is how positive definite matrices are defined, right? So this part will be quadratic form of Q, and this part will be quadratic form of R, which means that for positive definite matrices, R and Q, which we defined here, they also will be symmetrical in our case. Both these terms will be positive, always, for any T, all right? So you have something positive plus something positive, you also get something positive, right? So we're minimizing some of those two positive terms and how it looks like, for example, when Q is diagonal. So Q equals to something like that. Diagonal matrix. Obviously, all of these numbers must be positive because for diagonal matrix, these are eigenvalues of the matrix Q, and matrix Q is positive definitely, so all of the eigenvalues are positive. Right? So positive numbers on the main diagonal, and you have X transpose QX. So what that thing will be? Actually multiply and see, but it's a very simple expression actually for diagonal matrices. It will be Q1 times X1 squared plus Q2, X2 squared plus X3, X3 squared times Q3 and so on. It's just weighted sum of the squares, which means if you put it here, it will be weighted sum of the energies of all x's. Similar to here, okay, for a single u. You'll have r times u squared plus q1 times x1 squared plus q2 and so on. So this is weighted sum of the energies of all of the states. You can have also energies between the states, which is like x1, x2. So all of the off-diagonal values here, okay, if they are not zero, you'll have also components of like x1, x2, x1, x3, x1, x4, and so on. So you have also this values weighted, but you don't have to, right? And typically we are choosing the matrix to be diagonal for simplicity. But sometimes you have some cross links between x's that you also want to consider. Depends on your system, what you want to optimize, okay? So to summarize, this term is penalized as a transient state deviation from the origin, which means that your states x will have some values which are going up and down, and they need to converge to zero eventually when you have zero input, okay? So this penalizes how fast it goes to zero and converges all to zero, because eventually they all need to for linear systems. For all linear systems, states always converge to zero with zero input from some initial conditions, okay? And this is penalizing control effort, which means your U energy. Now, you will need to play with these numbers in matrix Q and matrix R to get the benefits of both worlds practically. So if your U is too strong, too high, increase R a little bit until you get it in the right range. And then this is the best you could get for your R, for your X, okay, for your state. So this is the optimal solution. So it's actually not single optimal solution, it's like infinite number of possible optimal solutions here for different values of Q and R. But for each chosen Q and R, we will show that there are conditions for uniqueness of optimal controller. So you have only one possible controller out of all possible controllers, okay, which would be optimal for that given Q and given R. All right, so you have a unique solution for that problem, which is interesting in itself. So number one that you need to remember that J that we are optimizing is weighted sum of the energies of state and of the input of the plant, okay? And we are minimizing the J, and optimal controller will minimize the J. So we want to design controller which will be U of t equals to minus kx of t, which is regular controller. Pay attention that I'm not using the reference input. So typically you have minus kx of t plus r, which is a reference input, right? But I have zero input, so it's regulator problem first. We are not doing tracking problem. So it will be just minus kx. This is your closed feedback loop from the state. So you're taking states, multiplying that by optimal controller k, returning it back as dot product between k and x. That's it. As before. I mean, this is the same state space controller that we used before. But now, practically speaking, we converted one problem into another problem. Technically, this is how optimal control works. Have we really solved the problem? Because previous problem was like, where do you put the poles? Now we do not have that problem. We will put poles wherever they are to minimize that thing. But in that case, we need to choose what R and Q are, which means we had one problem where to put the poles. Now we have a problem like what Q and R you need to choose. Why that problem is better than the previous problem? What do you think? Why is this approach is kind of more practical? Why people using that approach and not the previous approach most of the time? Yes.
Basically, you have removed half of the constraints, like for example, from Q and R. If instead of considering all the possible values, now we will be considering only few values of Q and R, other Q and R values. Anyway, we have this.
Well, not really, because Q matrix is n by n. You have like n squared plus, even for CISO systems, you have n squared values here to choose plus R, which is n squared plus 1 values to choose. And in poles, you need to choose only typically half of them or close to half of them, right? Because if some of them are real, you put them on real axis. If they are imaginary, you have pairs which are exactly the same conjugate values, right? So you kind of actually need to figure out more numbers here than before. But the choice here is easier. This is the same. Again, typically you're choosing, unless you know something about your systems, that you have some weird mechanics between different axes and they correspond to different things, and they have some link between them in a way. Typically you're choosing that matrix diagonal, so you have only n numbers to choose here, plus one number for R, for CISO systems at least, okay? But this is not the issue. The issue is that you can run it with pretty random selection first. Okay, let's say this one is all ones and R equals to 1. Okay, you just start with some random selection of values. For diagonal values here, zeros everywhere else, R equals to 1. Okay, and you get particular x's and you get particular u in time. So you simulate the system in time, you get particular functions of time, right? So you look at these functions and you're saying the following: this function is too high for me, so I cannot afford having that huge u or that huge x, right? So you know what these things are, right? Because you designed the system. So you know how strong or high should be your values. What are your limits, physical limits on your system, right? So you're saying, for example, u is too strong. What should you do? You are bumping up the R, right? So trying stronger R, simulating the system until it gets to a particular normal level where it needs to be, okay? So it's easy to play with that number. Now, given that knowledge, now, for example, one of the x's is too strong, okay? Or multiple x's are too strong. Just pump up the appropriate coefficient here, which like pull it up, and you'll have smaller x, okay? That's it. This is how you design the system in general, okay? So it's much more intuitive, like what numbers you need to change and where you need to move them. But we will learn also additional technique. We will learn symmetrical root locus, which will tell you where your R needs to be to give you particular performance or particular location of poles or whatever you need, okay? So you will see entire trajectory of the optimal poles in root locus space. So you'll see like where they move as a function of R in general, okay? And how you minimize also y squared, which is energy of the output instead of energy of the axis, which is kind of easier to work with, right? Because for axis, you might not even know what are the boundaries, reasonable boundaries for your system. But for y, which is output of your system, you typically know where it's supposed to be, right? How it should be. So we will convert all of that into even simpler problem, okay? Again, this is the thing that we talked about, that if you're doing quadratic form of that matrix, this is what you get, it's just weighted sum of squares. All right? Any questions? Okay, so this is a theorem which we will not use very frequently. We almost always assume that this is true because this is not too difficult to conform to these conditions. But this is uniqueness and existence of controller, optimal controller. So controller, these are necessary conditions and for existence and uniqueness of the controller, optimal controller, which means when the system will work. And I haven't showed the system yet, like the actual process. But this is telling you when the process will work, okay? So it will work if pair of matrices A and B is stabilizable, which is obvious, because if system is not stabilizable, nothing could be done. It's not only optimal controller cannot be built for that, any controller cannot be built for that. System will diverge. That's it. Non-stabilizable system is not possible to stabilize, period. Right, so it's kind of obvious condition that needs to be there. Okay, R should be positive, definite, and symmetrical, which is also obvious because you need weighted sum of positive numbers for minimization to work, right? So R will be positive, definite, and symmetrical. And Q will be positive semi-definite. And positive semi-definite, which means should be the other way around. Actually, it should be larger here, larger or equal. Oh, no, this is correct. This is 0, smaller or equal to Q. So Q is positive semi-definite. Okay, so this is correct. So for ZQ, this is another condition how you define positive semi-definite. It could be written as multiplication of two matrices. Okay, so it's like, think about that as it's possible to make square root of it in a sense, but in matrices in a way. So this is how you write square root in matrices. Okay, so if you write that square root of the matrix Q, which is that matrix C, it should be together with a detectable pair, which is the most trickiest condition here, like to visualize what it all means. Okay, so the component of matrix Q, which is like one matrix times another matrix, gives you matrix Q, which is positive semi-definite, and that part of it together with the matrix A should be detectable. Okay, it's tricky, but that's okay. This condition is almost always true for most of the systems. Okay, so how do we design continuous time optimal controller first? All right, here we have a theorem that we'll actually prove, very interesting theorem, which says that optimal controller K, which is given by U of T equals minus Kx, regular state space controller, given by that formula, which is R inverse. R, you know what that thing is. This is weight of the energy of the inputs, right? So R inverse, and since it's positive definite, you can make inverse of it, right? So you can make R inverse times B transpose, which is matrix vector for CISO systems or matrix for MIMO systems, times S. So what is S? S is positive definite matrix, which solves the following continuous algebraic Riccati equation. That equation. This is definitely matrix equation, right? So all of that is matrices. S is matrix of n by n, A is matrix n by n. So it's like system of n by n in matrices. But pay attention that here you have mistake. This is supposed to be S here. Okay. So pay attention that this system here has S squared, right? So in a sense, like you multiply S by S. So elements of S will somehow be multiplied by themselves in a way, which means that you will have, instead of regular linear equations, you'll have quadratic equations. This is not linear algebraic equations. These are systems of quadratic equations, many of them, all right? And by n of them, typically. Okay, so you have a lot of quadratic equations here. So you'll have huge system of quadratic equations that you need to solve them to find the matrix S. And matrix S is symmetrical and positive definite. Obviously, for system of quadratic equations, you have tons of solutions. It's not single possible solution and not infinite number of solutions or no solution, which is true for linear equations. If you have system of linear equations, you have three choices. One solution, unique solution, infinite number of solutions, right? Or no solution at all, if the system is self-contradictory in a sense, right? We've seen that before. But in that case, you have multiple normal solutions. You have many of them, all of them solving that system of equations. But if all of the previous conditions that I mentioned in the previous slide are true, you will have only one optimal solution for which S will be positive, definite, and symmetrical. All right, this is the beauty of the previous condition. So you will have tons of different possible solutions using these quadratic equations, but only one of them will be positive, definite matrix. Okay, everything else will be not positive, definite matrices. And this is unique solution. More than that, this theorem states what will be J in that case. So in that case, J minimum, which is the optimal J, right? Optimal criteria, cost function, optimal cost function, will be X0 transpose, which is initial state transpose, it's constant vector, times that matrix S times initial vector, state vector. Okay, this will be your value and it will be number, right? It's again, that same is quadratic form. So it's positive number. So J will be some positive number, and you can compute it based on that, based on your initial conditions. So for different initial conditions, you'll have different J, but they will be optimal J. Okay, all of them. If you found that unique matrix S, which is positive, definite, and symmetrical. Okay, by solving that equation. So remember that this is called continuous algebraic Riccati equation. Sometimes people just say it without C, so they are saying ARE or CARE or AIR or whatever you name it, ARE, algebraic Riccati equation. Okay, we will have also discrete algebraic Riccati equation, okay, for discrete time systems, which will be different thing, but still same kind of thing. All right. So for CISO systems, we can write our criteria also in a different way. If you choose Q equals to C transpose C, which is very interesting and specific choice that you need to remember, because we will be using that a lot, see what we get here, okay? So let's say R equals scalar value of rho, it's just some number, okay? And Q, we decided to make it C transpose C. All right, so far it's just particular choice of matrices Q and matrices R, right, for CISO system. Typically, we will use that choice because it's a very convenient choice. And I will explain in a second why this is convenient choice. This is convenient choice because J will look like that then, right? It will be Y squared, which is output squared of the system, plus rho times U squared. So it's practically weighted average between energy of output plus rho times energy of input. So it's very convenient to think about some type of input-output relations. So we are optimizing weighted average between output energy and input energy. This is what the thing is. And why is that for that choice happening? Let's see. So if you remember in that thing, you had X transpose QX plus U transpose RU. So again, for CISO systems, this is just R times U squared. So you get that part. The thing is just U times rho times U. So it's U squared times rho, right? This is scalar, so you can multiply them. But what is X transpose QX? I'm replacing, substituting Q equals to C transpose C. So you'll get that instead of X transpose QX, right? So you can think about that as this thing transpose in inverse order. Remember that AB transpose is B transpose times A transpose, right? So switching the order and making transpose of both. This is linear algebra. So you get practically CX transpose times CX. But what is CX? CX is Y, right? So it's Y transpose times Y, but Y is scalar for CISO systems, right? So y transpose is y, because it's scalar. So it's y squared, right? So you get that entire thing, it's just y squared plus rho u squared. And this is why I can write it that way. Any questions on that? And we will be using that particular criterion almost all the time because this is the easiest to use by hand. This is kind of after some simplifications, but you need to remember that you can do exactly the same tools for full Q and R as they are. You can have not only diagonal matrices, you can get anything you want. So the entire theory works for any kind of matrices, positive definite matrices. But we will be using that criteria for simplicity. Okay. Before I will prove the actual theorem here, hopefully at the end of this hour. But before that, I want just to mention a few more criteria that you can use. And for them, you have other conditions and other Riccati equations. Okay. By the way, Riccati worked on these equations long before controls were invented. I think it was maybe 1700 or something like that. It's like many years before any controls were invented in general. So it was for completely different purposes. People just use it much, much later. So here's another criteria. This is a generalization of the optimization criteria. And it looks like that. So J will be X transpose U transpose times some block matrix with additional blocks of N and N transpose, Q and R, X and U. Or more explicitly, it will look like that. So before that, we had that part and we had that part. Now I'm adding cross-linking between X and U as well, okay? So you might have that part as well and that part, which are kind of symmetrical, but you have some additional part which you can optimize if you want to, like multiplications of pairwise U's and X's, if you care about multiplications like that. And sufficient and necessary condition for that will be A, B controllable, this two matrix detectable, and W is at square root of that particular matrix, okay? Complicated, we will not get into that, but you can, like I'm showing that example only to demonstrate that these are not the only possible cost functions that we can minimize. We can minimize all kind of cost functions. These are just the most popular ones, and I will show in a minute another popular function which is actually useful, more useful than this one, I guess. But you might find uses for that as well, okay? Practically, I haven't used it ever. But maybe you will find some use for it. So the optimal solution will be exactly similar to the previous one. You have Riccati equation like that. And solution S will be inside the K. So K will be some R inverse times ZC. Okay, bigger formulas than before. Similar to the previous one, you just add in the N transpose part. Okay, but this one is more interesting, more important, which is called prescribed degree of stability. So the idea is that you want your system obviously typically to be as fast as it could be. Okay, so you can push the entire thing, or in a sense, what you want to be is not only stability of the system to be promised to you, but also at least particular performance in terms of settling time. Okay, so settling time starts from here to there. And if you remember, settling time in terms of pole location would be how far to the left your poles are, all of them. Farther to the left means faster poles in continuous time system, right? So the idea here is that you can add that term to that J function, which is exponent of 2 alpha t, and alpha will be additional coefficients that you can play with. And this alpha will be distance to the closest pole on the left, okay, in the left semiplane, which means you will try to push all of your poles behind that alpha line. This is the alpha distance. So all of the poles will be here somewhere. Okay, this is J omega. This is the overall idea, okay? And for that, the design of the function will be like that. So to get that, you need that kind of coefficient, all right? practically it will say that everywhere in all of the Riccati equations, in all of the controller solutions, optimal controller, you'll just replace matrix A with matrix A plus alpha I. Okay, this is what it means in practical terms. Same controller, you see, but Riccati equation, I just replaced everywhere where I had A, I replaced it with A plus alpha I. This is a solution for the new S. Okay, and what that thing means, like what are the eigenvalues of that matrix compared to the A matrix? You just take the original matrix and shifting all of the eigenvalues to the left by alpha. This is what it means. Like if you're adding constant number to the diagonal of a matrix, you're practically shifting all the eigenvalues to the left by the same number. If all of them added the same number. Again, linear algebra. Okay, how you shift particular eigenvalues. Okay, so we learn a lot of different things about linear algebra more than about controls, but it all connects together somehow. Okay, so existence uniqueness, again, you're doing exactly the same thing like with the original theorem, but for A plus alpha I matrix. Okay, everything else is the same. All right, so this is very useful. Why? Because you can decide that you want your poles to be as fast as you want, at least as fast as alpha. Okay, and then optimize on the, like compromise on the U and Y. Right, then you can play with these two values, or X and U energies. All right, within that constraint that all of the poles will be far enough to the left. Okay, so this is very helpful actually, because sometimes like to get minimal U, you need to compromise a lot on X, right? And you do not get performance that you actually wanted in the first place, because your system is not really close. All right. Any questions on that? And the last thing in the theory, before we get to actual theorems and proofs, as we love in that course, right, is discrete time optimal controller, which you can implement in the computers for discretized systems. So here's how it works. This is your discrete time system, as usual. Your optimization criteria, instead of integral, I have sum, infinite sum, for obvious reasons, because all of the states are discrete. And again, the mistake here is that this should be also a function of n, of course. So all of them supposed to be n here. Okay. So all of them are obviously discrete. Okay, all of these functions. Again, same thing, exactly the same thing as it was before, just for discrete variables. That's it. And the solution will be a little bit different. And it will look like that. K will be given by that more complex formula, where S is a solution of discrete algebraic Riccati equation. And this algebraic equation is given here. Okay, just more matrices to multiply. But still you have the same thing. You have multiplication of S by S, so you'll have equations which are quadratic equations, system of quadratic equations, not linear equations, for the Riccati equation. And same J minimum, x0 transpose times S times x0. Okay? Any questions on that? So in MATLAB, it's like one line in implementation for each one of them. You have functions to find solutions to Riccati equations, which are the first two functions. You can function to find optimal LQR controller, which is a third function, discrete LQR controller, which is one before the last function. On that optimization with y squared plus rho u squared is the last function. You can just go to help and you'll find all of these functions. It's just one line, you put images as A and B, and like what your Q and R are, and then you get the solution, period. This is how easy that thing is, okay, in MATLAB. So all of that was implemented for you, but we will do next time, next lecture, we will actually solve by hand a few examples that you will appreciate how easy it is to use MATLAB, right? Because this will be kind of nightmare to get to the solutions, even for 2x2 systems. If you're doing things by hand, and people did it by hand for much higher order systems, because in 60s, people didn't have computers to do all of that computation and optimization. So let's go back to the original theorem, which is that thing, okay? And let's try to see why this is true, all right? So I will start with small lemma and define in the lemma additional term. Let me see. So I will stop that thing. Making troubles. Okay. So let's start with proving the theorem that this is the optimal control direction. So I'll start with lemma. What is lemma? Do you know what lemma is? What is theorem? You don't know what theorem is? In math? What is theorem?
It's a statement that proves something, that anything, like for example,
It's statement, yes, it is statement that could be proven based on what?
based on few conditions, like for example,
Based on few assumptions.
assumptions.
So you have some assumptions, you have some axioms, which means something which is acceptable without proof, typically. And based on these axioms, you can prove some theorems. So theorems are statements which are more complex than axioms, because axioms, we just accept them on belief level. We just see that this is true, we accept them as they are. Okay, so 1 equals to 1, it's obvious, you don't need to prove it, right? But more complex things, we are using the basic axioms, basic assumptions. And then based on these assumptions, we are concluding logically some theorem, right? So what is lemma? Lemma is kind of small theorem. So lemma is theorem which is helping to prove another theorem, which means it's like helping tool in a way. So it's like before you prove the big theorem, you need some sub-theorems which are helping you to put together the bigger proof of a bigger theorem, okay? So lemma is kind of small theorem. All right, so this is my lemma. It's about controllability gramian. Okay. Oh, P. This is integral from 0 to infinity of exponent of A tilde transpose T Q tilde an exponent of A tilde T dt. Okay. This is how it is defined. Okay, so it's integral of some sort of exponent times q times another exponent. Looks complex, but I will connect it. So the lemma states that this Gramian is solving the Lyapunov equation. That this is for stable A tilde. Remember Lyapunov equation? This is where we actually use it. So I found for you explicit solution for Lyapunov equation, which always solves that Lyapunov equation, whatever it is. Okay? For any stable A. So this thing, which is the integral of this exponents and all the other stuff, will always solve that particular equation. And we will get to why I'm using everywhere tildes. Okay, because this is not the original A and Q that I will be using. I will define different A and Q for the theorem, and then I will just redefine them in terms of tilde. Okay, it will be kind of like closed loop A type of thing. Okay, this is overlaid. And I will tell you why that thing is important, like why we need that type of lemma a little bit later. But first we want to prove that this is true. Okay, why this is correct. So let's just substitute and see if it works. Okay, this is the easy proof, right? So A transpose P plus PA equals integral from 0 to infinity A transpose exponent transpose T Q tilde exponent A tilde T plus exponent A tilde transpose T Q tilde So let's see, what do we get here? So you have A transpose. Since this is constant matrix, it can get inside the integral, right? So inside the integral, you have that Gramian, which is a P part. Okay, this is a P part, right? And now you have P, which is again integral on that thing, and sum of the integrals is integral of sum. So you don't have to write here additional integral. You can, but you don't have to. I made that thing already, okay, because it's linear. So it's that P part times A tilde, which is coming from here. And then I'm closing that with dt. Okay, so far? So I practically substituted that thing inside. All right. And here's the trick. This integral from 0 to infinity, d to dt of that thing. So if you compute derivative of that thing in matrices, this is chain rule. You get that. Exactly that. Okay. It's all the multiplications from left and right. So chain rule in matrices works exactly the same way it works in regular functions. But you just need to remember to multiply from the right or from the left when you're multiplying by the chain, right? This is the difference where you need to be careful. But believe me, this is correct, okay? You can try that at home and see how it works. You have two variables of t, so you're taking all of the first part, you'll be multiplying by that internal derivative, right? And second part will be multiplied by the right by that internal derivative. Okay, remember that rule, chain rule? Okay, so integral of derivative, what that thing is? The function itself, right? Main theorem of calculus. All right, so what you get here is E A transpose T Q E A tilde T between T equals to 0 to infinity. All right, and here's where stability comes into that question. Why this needs to be true? Because for T equals to 0, this is E to the power of 0, right? And this one is also E to the power of 0. So this is for T0. But for T infinity, what happens when T goes to infinity? You want that thing to converge to 0, right? So that entire thing converges to 0, and that entire thing converges to 0. So it will be 0, and this will be true only for stable matrices, obviously, because for unstable matrices, this will go to infinity, right? But for stable matrices, that exponent will converge, and that exponent will converge. So it will be 0 minus q, right? At t equals to 0, you'll have 1, 1, or I in that case, right? So this will be equal to I, this will be equal to I, because t equals to 0, right? And times q, so it's minus times q tilde, which is minus q tilde. That's exactly what you wanted to do, right? So this is that equation. So done with the proof of that thing, okay? But this is just lemma. So I showed that that controllability gradient solves that thing for stable matrix A, tilde. Okay, so far? All right, so now let's move to the next part. The next theorem says proof of the controller theorem. Camera. Okay, so we have a few assumptions. Q is positive, semi-definite. R is positive definite. And AB stabilizable. Right? We need to prove that K equals minus R inverse P transpose S is minimizing J, where S is solving that equation. This equation will be A transpose S plus SA minus S B R inverse B transpose S plus Q equals to 0. Pay attention that this is not scalar 0, this is matrix 0. All of them are matrices n by n. Okay, so far? So that's what we want to prove. So how do we do that? So let's start with the J. So our J is integral from 0 to infinity x transpose qx plus u transpose ru dt, right? And our u is minus kx. All right, this is how we design the controller. So I'll just substitute the u here and here. So let's see what do we get. We get integral from 0 to infinity x transpose qx plus u transpose will be minus kx transpose r minus kx. Okay. So this will be integral from 0 to infinity x transpose qx. So this could be replaced by plus and plus, right? This should be switched to have x transpose k transpose r and then kx. All right. Now, you can take x transpose on the left side and x on the right side out of the parentheses because they both have the component here and here. All right. Then you'll get this integral from 0 to infinity x transpose. Then you'll have q plus k transpose times r times k times x dt dx t. Okay. K transpose r k x. Okay, so far. All right. So this is our first part. So we've got two particular quadratic form, right? So this integral of the quadratic form should be minimized. Now, so what is our x? Remember, solution for the x is given 0 input. So you have system which is closed loop system. So what is our closed loop system? X dot equals what matrix? So for 0 input, this is our system, right? And let's call x0 is x at time 0 for the system. So what is solution of that system? Explicit solution that we discussed before. Remember the solution? This is explicit solution. Okay, so it's exponent to that matrix or whatever it is for any system. Okay, it's like for any linear system. This is explicit solution for any system with any matrix here. This exponent times x0 for any 0 conditions, and then you have plus convolution integral here if you have input, but you have no convolution integral because you have no input, right? So you have just the initial part, response to initial conditions, which is an exponent that we defined before. So let's substitute that thing here and there. Okay, need space. Okay, so this integral from here from 0 to infinity, okay? And now we substitute that thing. That will be exponent to the a minus bk t x0 all of that transpose q plus k transpose r k and exponent again a minus bk t camber a little bit. N times x0. Okay, so far. Now, if you are making transpose here, you will replace that with x0 transpose and exponent of a minus bk transpose t, right? So x0 is constant, so it can go outside here, and here x0 is constant, so it can go outside here, okay? So what is left inside we will define as s, which is interesting, because this will give us, and we do not have time to solve it today, we will continue proving it next time, but it will be, practically speaking, x0 transpose times s times x0. And if you remember, that's exactly how the theorem stated it to be. Okay, this is optimal J minimum, and that entire integral in the middle with all of these exponents and q things and other things will look exactly like this one, right? So A tilde matrix will be A minus BK, and Q tilde will be that thing inside, right? And this will look exactly like that. And since we know that this thing, which is at S, is solving Lyapunov equation, okay, we will show that it is optimal, okay, but next time.